In the red centre of Australia, far from the opal towns, sapphire fields and gold rushes, there is a gemstone that looks almost impossible. At first, it may appear to be a pale piece of feldspar, cloudy, simple and easy to overlook, but then the light hits it. Suddenly, black lines appear inside the stone, sharp blades, triangles, geometric patterns. Then a golden metallic flash sweeps across it, tilted again, and a colour erupts from within. Blue, green, orange, pink and violet, as if a rainbow has been trapped inside the crystal. It looks artificial, it looks carved, it looks like some kind of natural circuit board, but it is completely natural. This is Rainbow Lattice Sunstone, one of the strangest gemstones on Earth. The classic material is known from one tiny area in Australia's Northern Territory, and the reason it is so rare is not just because the deposit is small. It is rare because the geology had to be almost perfect. The crystal had to form with the right chemistry, it had to cool in the right way. Iron had to separate inside the feldspar along precise internal planes. Later, some of that iron had to oxidize, creating flashes of metallic fire and colour without destroying the stone. The result is not just a gemstone, it is a geological accident preserved in light. Rainbow Lattice Sunstone begins with one of the most common mineral groups on Earth, feldspar. That might sound underwhelming, because feldspar is everywhere. It forms huge parts of granite, gneiss, pegmatite, volcanic rocks, weathered soil and sand. It is one of the great rock-building minerals of the planet. Most of the time, people walk over feldspar without even noticing it. But in one tiny part of Central Australia, ordinary feldspar became extraordinary. In the Harts Range, northeast of Alice Springs, feldspar crystallised in a way that produced one of the rarest optical effects in the gem world. The classic Rainbow Lattice Sunstone comes from the Rainbow Caterpillar mine area. This is remote country. Old rocks, red dirt, desert heat and scattered mineral occurrences exposed by millions of years of erosion. The host mineral is a potassium feldspar, commonly described as orthoclase. Chemically, it is a potassium aluminium silicate, with the formula KLSI308. On its own, that formula does not sound dramatic, but the magic of Rainbow Lattice Sunstone is not just the feldspar itself. The magic is what formed inside it. When the feldspar crystallized, tiny amounts of iron were locked within the crystal structure. As the stone cooled, its internal chemistry began to reorganize. Minerals that were once mixed together at high temperature started to separate into microscopic structures. This process is called exsolution. Exsolution is one of the hidden engines of gemstone beauty. It can create fine internal layers, films, and intergrowths that bend, reflect, and scatter light. In Rainbow Lattice Sunstone, this process helped create a soft internal glow similar to moonstone. That glow is called iridescence, but the moonstone-like glow is only part of the story. The most famous feature is the lattice. Inside, the feldspars are extremely thin, oriented inclusions of ironstones, mainly magnetite and hematite. These inclusions did not form randomly. They grew along specific crystallographic planes inside the feldspar. In other words, the atomic structure of the host crystal controlled the way the inclusions were arranged. That's why the patterns look so precise. The dark blades and triangular shapes are not cracks. They are not scratches. They are not artificial engravings. They are tiny mineral inclusions arranged by the geometry of the crystal itself. This is what gives Rainbow Lattice Sunstone its almost alien appearance. We are used to seeing nature form curves, grains, clouds and irregular textures. But here, nature forms straight lines, repeating patterns and sharp triangles. It looks designed because crystals are natural geometry made visible. The stone also displays aventurescence, the glittering sunstone effect. This comes from reflective hematite platelets inside the feldspar. When light strikes these thin metallic inclusions, it flashes back as gold, orange, bronze or red. That is the sunstone part of the gem. But Rainbow Lattice Sunstone is not just a sunstone. It can show the glow of moonstone, the sparkle of sunstone, the dark lattice of magnetite, and the rainbow colours produced by light interacting with thin internal films. Move the stone one way and it can look dull. Move it slightly and the whole interior comes alive. This is why the gem is so difficult to capture in a still image. A photograph only shows one angle. Rainbow Lattice Sunstone performs as it moves. The deeper story is even more fascinating. In many deposits, unusual minerals form because hot fluids move through rocks and deposit new material. But Rainbow Lattice Sunstone appears to have formed much of its internal structure from within the feldspar itself. The iron was not simply painted into the crystal later, it was already present in tiny amounts, then reorganized during cooling. That means the stone built its own lattice. As the pegmatite cooled, feldspar components separated, fine internal films developed, iron gathered into magnetite along specific planes. Later, weathering and oxidation converted some of the magnetite into hematite, adding the metallic flash and helping produce the colourful optical effects. This required an incredibly specific chain of events. The original pegmatite had to contain the right feldspar. The feldspar had to contain the right trace elements. It had to cool slowly enough for internal structures to form, but not in a way that destroyed the effect. The iron oxides had to align with the crystal structure. Then the stone had to survive alteration, weathering, cracking, and erosion. Most rocks fail at one of those steps. The chemistry is wrong, the cooling history is wrong, the inclusions grow too randomly, the crystal fractures too much, the effect is too weak, or the stone simply weathers away before anyone ever finds it. But in this tiny part of Harts Range, the conditions lined up. That is why the classic Australian Rainbow Lattice Sunstone is so special. Ordinary sunstone is found in other parts of the world. Other feldspars can show flashes, colours, or interesting inclusions. But this particular combination, the lattice, the rainbow iridescence, the moonstone glow, and the sunstone flash, is tied to this remarkable Australian occurrence. And because the source is so limited, good material is scarce. Mining is small scale. The feldspar must be dug, sorted, washed, inspected, and selected by hand. Much of the rough is fractured. Much of it does not show the ideal lattice. Even when the material is good, it must be cut carefully, because the optical effects depend on orientation. Cut the stone the wrong way, and the magic can disappear. That makes fine pieces rare twice over, rare in the ground, and rare after cutting. This is why good Rainbow Lattice Sunstone can sell for significant prices. Small pieces and lower grade specimens may be relatively affordable, but fine cut stones and high quality collector pieces can reach hundreds or even thousands of dollars. The strongest stones show clean patterns, bright rainbow colours, golden flash, and a sharp lattice that appears to float inside the crystal. The name has also created confusion. Some stones from other countries are sold under similar names, including lattice-like feldspars from Tanzania. These are not necessarily fake stones. They may be natural and attractive in their own right, but they are not the classic Australian Rainbow Lattice Sunstone from the Harts Range. For collectors, origin matters. Because the real story is not just the look of the gem, it is the place. A remote Australian pegmatite, a rare feldspar chemistry, internal exsolution, iron oxides growing along crystal planes, oxidation adding colour and flash, millions of years of erosion exposing the material at the surface. Rainbow Lattice Sunstone is a demonstration that some of Earth's rarest treasures are not made from exotic ingredients. Sometimes they are made when common ingredients experience an uncommon history. Feldspar is ordinary, but this feldspar recorded a perfect sequence of geological events inside itself. Every black triangle is crystallography, every golden flash is iron oxide, every rainbow is light interacting with microscopic structure, and every good stone is a tiny window into a process that almost never happens. That is what makes Rainbow Lattice Sunstone so compelling. It is not just a gemstone found in Australia. It is a natural optical machine. A sunstone, a moonstone, and a geometric lattice stone all in one, formed when the chemistry of feldspar, the behaviour of iron, and the deep history of the Harts Range came together in one extraordinary piece of Earth. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.